No, it's hard. Don't get me wrong. I agree with you. It's hard. But it's still very much satisfactory. Chemistry 1 and 2, you know, you're not learning chemistry 1 and 2.
So did you enjoy the pointing vector? Was that exciting today? Absolutely, right? So, I prepped you last time by talking about plane waves, right? And how plane waves are how we model electromagnetic radiation. So, what you saw in today's flip is these properties of electromagnetic waves, sorry, achievements, they're not flipping, is that we talked about an electric field having some maximum electric value, right? And then it depends. Remember, this can be y as a function of x, or it could be y as a function of t. In the y as a function of x scenario, then the actual amount of electric field value is dependent on the length of the magnetic, of the phasor at that location. So these waves are like electric field phasors. Remember, if you have something of a constant magnitude and it goes around in a circular pattern, it will swipe out a wave pattern where the maximum value is the maximum strength of the electric field, if that's the generator. Nothing is actually going up and down, right? It's just increasing in strength and decreasing in strength. But there is a dx distance where one end of this will have an electric field E, and the other end will have an electric field E plus dE. So over this dx thickness, there's an E plus dE flux change, which induces a magnetic field perpendicular to the plane of it. Where the frick does this come from? Maxwell's equations, right? Remember how we're getting to the Maxwell-Ampere law, which says that mu naught epsilon naught d flux E dt. If there's an actual flux change over a distance that happens over time, that will induce a B because of that. That's what this equation says. Right? If there's a changing flux over some area, and that changes with time, you will get a magnetic field from it. That magnetic field will be perpendicular to the plane of the changing electric field strength, even though it's not actually going up and down. It's its mathematical representation. This B then will, if you study it, as this guy changes with time, there will be a B over this region, which has a different strength. Now, if we switch to the y versus t axis, this becomes a dt distance, and there's some value B here on this end of the rectangle, and some value B plus dB here, because this strength is increasing and decreasing sinusoidally, in the plane, like this, right? So this is meant to be in the plane. This guy then will reintroduce an E in this direction, which reinforces that one because of the right-hand rule, right? That E creates an I. So that E is the E dot ds that replaces the script E in the negative d flux by dt from Faraday's law of induction. So this is a mutually inductive relationship. The electric flux change induces a magnetic field to be created, which is also changing with time. Therefore, the changing flux reinduces the electric field that created it in the first place. So this is the process known as electromagnetic induction. And the wave of the energy travels in this direction. It's given the value called the Poynting vector. And the relationship of the Poynting vector to the electric field and magnetic field, these guys always must be perpendicular. E must be perpendicular to B because of the nature of the relationship. And you get this value of the Poynting vector by taking 1 over mu naught times E cross B. And this is known as the intensity of the wave, or the flux, the 4-letter F word of physics, right? Flux. nobody gets what Flux is. Question?
Yeah, I was wondering for the lines.
I'm sorry?
For the line heat, right?
Yes.
He's pointing straight up and he's pointing out towards.
Right.
What does the straight